Thank you all for coming today. So the rain stopped and the clouds parted just in time for our class. I think it's going to be a good day of chemistry. All right, so the exam, as you all know, is coming up next week. So I'll give you your final reminder about tomorrow's exam review session, which is going to be 2 p.m. in SEC 102. I encourage you all to come. It will be recorded if you're not able to make it. And you can plan on it being around 1.5 hours or so. It's hard to predict exactly how long, but that's about how long they usually take. The other thing that I'll mention before I start is typically before the exams or during the exam, which will again be next week, Monday through Wednesday, there's a increased demand for office hours. So I will try my best to make myself more available for that, make it more flexible for all of you. So today, if you want to come see me after class until 3 p.m., I should be in my office and be free. Tomorrow, I'll be around for about 2 hours before the exam review starts. So if you come between then, I can talk to you individually. Monday and Wednesday, I'll only be available on Microsoft Teams, not in person in my office, but you can contact me anytime and I should be available most of the day. So just give me a little bit of advance notice and we can set something up online, Teams or Zoom if you prefer. Either one works for me. And we can go over questions and problems that way. And then Tuesday, I'll be available after class until about 2:30 p.m. and then 3:30 to 5. There's probably going to be a half hour in there somewhere where I'm tied up with another meeting, but I'll let you know exactly when that is once I find that out. All right, so there's going to be plenty of opportunities for you to come see me, so any last minute questions you have, please don't be shy about finding me and getting those taken care of. So we're going to continue today with material from Chapter 4, and the two topics, as it says, are molecular polarity and hybridization. All right, so to get into molecular polarity, so we talked last time about the VS-EPR approach, which is how we can determine the three-dimensional shape of molecules. And you may be wondering, why do we care about the three-dimensional shape of molecules? What good does that do for us? And there's actually a lot of things that come out of that 3D shape. We're only going to talk about some of them in this course, so it won't be entirely clear why the 3D shape matters until you've gone through more of your chemistry sequences. But nonetheless, the one thing we're going to talk about that's directly related to molecular shape is what's called molecular polarity. So first, let's do a quick review on polar bonds. So this is a topic that was covered in Chapter 3. It will be on the first exam, so it's good to review it now. So you'll recall a bond is polar whenever you have two different atoms bonded to each other that have different electronegativity values. So the polarity is going to be oriented towards the more electronegative atom, meaning that's where we're going to have more electron density. So the example that I started with in class was HF, a very simple, sorry, this connector is not doing great right now. All right, so we started with this example in class when we introduced this. So this is one we saw before, where you have hydrogen and fluorine. Fluorine is much more electronegative than hydrogen, so you'd have a dipole oriented between the two in that direction, or the other way to write this is to put a partial positive on hydrogen, a partial negative on fluorine. So that's what it means to have an individual bond that's polar. Two atoms bonded together, different electronegativity values, so the electrons are not distributed or shared equally between the two. And we also saw that we can predict how polar a bond is, the magnitude of the polarity, at least in a qualitative sense, which is determined by the difference in electronegativity values, which we call delta EN, is how we abbreviated it. So the bigger the difference in electronegativity values for the two atoms, the higher the polarity of the bond, or the more ionic character that bond would have, or the ways we kind of said that. So if we do this series of carbon-halogen bonds, carbon to fluorine, carbon to chlorine, carbon to bromine, and carbon to iodine, so carbon is less electronegative than all of the first three, fluorine, chlorine, bromine. So in all cases for the first three, you're going to have a partial positive on carbon and a partial negative on the halogen. And the magnitude of that dipole, how polar that bond is, how unevenly distributed electrons are, is given by the difference in electronegativity. So there's a bigger difference between carbon and fluorine, so that's the most polar. Carbon and chlorine next. Carbon bromine has a smaller difference in electronegativity. And then carbon and iodine have very similar electronegativity values, so this bond would be approximately nonpolar. Again, to the first approximation it would be, but in reality there's going to be some small polarity associated with any bond that has two different atoms in them. All right, so we can see that how big the dipole moment is, how polar the bond is, depends on the difference in electronegativity. So that's all stuff that we've covered before. So what we're going to cover today is how to define the polarity for an entire molecule. So not just for two atoms bonded together in a covalent bond, but for an entire molecule where we have to consider all the atoms in the structure and the entire three-dimensional shape. So molecular polarity is defined in a similar way, but instead of just applying to one bond, it applies to the whole molecule. So it's going to be an uneven distribution of charge over the entire molecule or a large portion of it. All right, so again, we're considering now all the atoms in the molecule, things that are more complicated than just simple diatomics. And we're going to consider whether the distribution of charge is symmetric over that whole molecule, or if it's uneven, then we say that the molecule has polarity or is polar. So in this course, we're also not going to talk a lot about why polarity is important. We'll see it a little bit later on, and you'll see it a lot in Chem 2 and organic chemistry. So again, all these sort of foundations we're building up will often come back later on, and the importance of them will become more apparent later on. One important thing about polarity that we'll cover later on in the course is that when you're talking about dissolving one substance in another, typically polar solvents will dissolve other polar solvents very well, and nonpolar solvents will dissolve other nonpolar solvents very well. So the classic example is water. Water is very polar. It's a polar solvent. It can dissolve a lot of polar or ionic compounds. So with that in mind, you can now answer this important question. So if a white bear and a brown bear jump in water at the same time, which one dissolves first? Yes, the white bear, because it's polar. Okay, there you go. So now you know that, and we can talk about how we actually define polarity for the rest of today. So that's right now the only important consequence of it we'll worry about. So there's a way of measuring polarity quantitatively, which is called the dipole moment, and it's measured in a unit called a debye. I hope I said that right. And it's sort of in fundamental units is. We're not going to really talk about the quantitative aspects of polarity too much, but just so you're sort of familiar. This capital C here is coulombs, the fundamental unit of charge, the SI unit for charge. So it's a very small value for an individual molecule, because molecules are tiny. So it's a product of the charge and the distance. So again, how unevenly distributed the charge is and over what distance that distribution is are going to both factor into the magnitude of the polarity. Again, we're not going to really deal with the quantitative aspects, but just to quickly introduce that. And we call this quantitative measure of polarity the dipole moment. And it's abbreviated with yet another Greek letter, which we may have seen. It's mu, which is the same Greek letter we use for micro, the prefix for units. Sorry, that should be mu. All right, so it's abbreviated as mu. So if you see that if you take a more physically oriented course, you might see that more quantitatively presented. But really the purpose that we need to fulfill in this course is how to look at a molecular structure. Again, looking at the formula, converting it to a Lewis structure, converting that into a shape, and putting all that together to figure out if the molecule is polar or if the molecule is nonpolar. That's essentially the level of depth that you're going to see in this course, in the stuff that we do on homework assignments and tests. So if we're going to predict the polarity of a molecule, the first consideration is that there must be polar bonds in the molecule. You cannot have a polar molecule that only has nonpolar bonds. All right, so what this means is that most polyatomic elements where all the atoms are the same are going to be nonpolar. So N2, P4, S8, these are all polyatomic elements, which we're going to, again, learn more about later in the course. Those are going to be nonpolar. Right, and that's because all the bonds in those molecules are nonpolar. It's the same atom bonded to itself, and when you have nonpolar bonds, you cannot have then an overall polar molecule. Now, there's one exception to this, which I'm not going to go into details on, but I encourage you to try to figure out why this is. If you've heard of ozone, which gets a lot of publicity for various reasons, which has the formula O3. This is a form of oxygen, but it actually is polar, even though it's all oxygen. So draw the Lewis structure of ozone, good practice for the exam, and then you can convince yourself why this one is in fact polar. But in general, if you have the same atom bonded to itself in diatomic like N2 or even larger structures like P4 or S8, it's going to be nonpolar. So for those ones, you don't really have to think too hard about whether it's polar or not. But in addition to whether or not it has polar bonds, you also have to consider the geometry. So the presence of polar bonds does not guarantee that the molecule will be polar. So you can have, and we'll see a lot of examples of this today, you can have more than one polar bond in a molecule, but that does not guarantee that the molecule itself is polar. So you have to again then think about the geometry. All right, so when you're thinking about molecular polarity, you'll need to consider the three-dimensional shape of the molecule, and then you'll need to decide whether all of those bond dipoles cancel out, in which case the molecule will be net nonpolar, or if they don't. So let's see how that works with a few different categories of molecules. So we're going to kind of go through this and try to recognize some patterns that evolve. So the first class we'll deal with are structures where you have no lone pairs on the central atom. So this would be an AXM-E0 structure where the central atom does not have any lone pairs of its own. And in this case, also it's important to note, what we're going to talk about in this part is that all X's are the same, one type of outer atom. We'll talk about the other case in a little bit. So if this is your situation, you have no lone pairs on the central atom, and all the outer atoms are the same, then these will all be nonpolar if they meet those criteria. All right. In some cases, it'll be obvious why that is. In other cases, it's not intuitive, but it's just helpful to remember that. So the simplest example that I can think of that shows this point is carbon dioxide CO2. So if we were to draw the Lewis structure of CO2 and then predict its shape, it would be an AX2 structure, which means it's linear as I've drawn it here. And if we think about the polarity of the bonds, though, we have carbon-oxygen bonds in this molecule, 2 carbon-oxygen bonds, and oxygen is more electronegative than carbon, so you're going to have a delta minus on each oxygen. If we're being careful about balancing the charge, technically this would be 2 delta plus. So each bond is polar, but what we see is that the dipoles are pointing in exactly opposite directions. All right, so again, if you're comfortable with vectors, this will make sense, but think about this as a tug of war. We have one oxygen pulling electron density towards itself, but we have the other oxygen pulling in the opposite direction, and those cancel each other out. So in that, this whole thing is going to be nonpolar. All right, and that's because even though we have individual bond dipoles, they're oriented equal and opposite of each other, so they cancel out, and in that, there's no unequal distribution of charge in this molecule. And that's going to be true for all of the AXM-E0 structures where there's no lone pairs on the center atom. For the rest of them, it's not as intuitive or as easy to visualize as this one, but it's going to certainly be true. So if we look at AX3, like BF3, each bond in this molecule is polar. This is trigonal planar, AX3. And in this case, your dipoles are going to all be pointing in sort of different directions, so you have to think about it in 2 dimensions. But if you decompose these vectors into x and y components, which is a step beyond what we really need to do in this course, but if you were to do that, you would see that they all add up to 0 as well, and this whole thing is nonpolar. And even the ones that are having more of a 3-dimensional shape, like carbon tetrafluoride, let me do that the same way I did it before. So this is a tetrahedral molecule, as we talked about last time, 3-dimensional, sort of a capped pyramid shape, if you want to think about it that way. This one is AX4. We have bond dipoles going in each of these 4 directions between carbon and fluorine, but they all cancel each other out. Again, not exactly obvious that that's the case, but it is true that in all of these basic shapes, AX2, AX3, AX4, which we show here, AX5, which is trigonal bipyramidal, or AX6, which is octahedral, if that's your structure, if all the outer atoms are the same, it will be nonpolar. So again, when you're answering questions on homework assignments and exams about polarity, most often what you're going to have to do is distinguish whether or not something is or is not polar. That's kind of the extent of what we'll normally expect. And so if it's a structure like this that has no lone pairs on the central atom, all the same outer atoms, then it can be, it'll be nonpolar. Now what happens though in the case where we still have no lone pairs on the central atom, but we have more than one type of outer atom? We won't encounter these as often in this course, but there are many compounds that would fit in this way. So let's think about a couple examples of this. So as one that's probably easiest to visualize, so I'll say a sort of a general statement before I get into the details. These are mostly going to be polar. Again, you have to think about the structure, draw it out, try to figure out if the dipoles cancel or not, because there are many possibilities here. Some of them will be nonpolar still, but in most cases, if you have more than one type of outer atom, you're going to have a polar molecule. All right, so as a simple example of this, let's look at the molecule COS. So it's the same structure as CO2, linear AX2, but we've replaced one of the oxygens with a sulfur. Okay? So in this case, sulfur and carbon have very similar electronegativity values. If I'm not mistaken, I think sulfur is a little bit more electronegative than carbon, but they're very close. So you might have like a really tiny dipole pointing towards sulfur in that way. But again, it's a mostly nonpolar carbon-sulfur bond. But as we said before, the bond between carbon and oxygen is significantly polar. So in this case, you have two dipoles pointing in the opposite direction, but they're different in magnitude. We have a large polarity between carbon and oxygen, a very small polarity between carbon and sulfur, so they don't cancel each other out in this case. And so in this case, you're going to have a net dipole that points left to right, as I've drawn it, where there's an unequal distribution of charge, more negative charge towards oxygen than sulfur, because oxygen is the most electronegative atom in this molecule. So this molecule would be polar. So it's still AX2, doesn't have any lone pairs on the central atom, but because it has two different outer atoms, those bond dipoles no longer cancel each other out. And then another one that would be AX4, or more, I guess, a more precise way of calling this is AXX prime, indicating that we have two different X's on the outer atom, but still a subcategory of AX2, or if we have AX2 X prime 2. So again, this would be in total AX4. If we had what's called dichloromethane, actually let's do a slightly simpler one. Let's just do AXX prime 3. So this one is CHCl3, which is called chloroform, has another molecule that has a common presence in the popular media. So CHCl3, that's called chloroform. So again, overall it's AX4, and again, as we said last time, if all the outer atoms are the same, AX4 would be nonpolar, but now we have two different outer atoms. So between carbon and hydrogen, it's a pretty nonpolar bond with maybe a little bit of polarity pointing from hydrogen to carbon. Carbon's a little bit more electronegative than hydrogen. And then carbon-chlorine, we have dipoles pointing all in this way. So again, the dipoles are unequal in magnitude and they don't perfectly cancel each other out. So this would be a polar molecule with the dipole pointing down, as I've drawn it here, towards the more electronegative chlorine atoms that are at the bottom. This one's three-dimensional, so it's a little bit harder to visualize. But imagine the dipole going straight down from hydrogen to carbon, right in between all the chlorines at the bottom. This is kind of how it would look. And again, you don't have to worry too much about the direction of the dipole or the magnitude of the dipole. You just need to be able to predict that it's polar. And this is a situation where the bond polarities, again, do not cancel out, so you would expect it to be polar. All right, so in many cases, if you have more than one type of outer atom, even if there are no lone pairs on the central atom, it will be polar. So that's an important one to think about as well. And then we're going to go on to structures that have lone pairs. And so if we have a structure with one lone pair, this will always be polar. All right, so again, it's helpful for you to think about why this is and still sort of visualize the three-dimensional structure and try to figure all that out. But they will always be polar if there's just one lone pair on the central atom. I should say on central atom is what we're talking about here. Okay? So that's another sort of easy category. If we're asking you to pick the molecules that are polar or nonpolar, if it has one lone pair, it's going to be polar, and that's as much as you need to think about it. So there's some common examples of this. For example, if we have NH3 ammonia, so ammonia has a lone pair and then 3 hydrogens, so it's going to be trigonal pyramidal. And so you would have the 3 dipoles pointing towards nitrogen in this case. Nitrogen is more electronegative than hydrogen. But you don't have the 4th one that would cancel out because there's a lone pair there, not another NH bond. So again, in this case, you'd have a net dipole. So this is an example of a polar molecule. Or if we go to, let's see, what's another one that's a useful example. I think SO2 would be a good one. It has one lone pair. Yeah, I think SO2 is one lone pair, sorry. So SO2 would be bent. You can draw it like this, or you can draw it with one single bond if you want to identify, obey the octet rule, but however you draw it, this molecule will be polar. It has one lone pair, and the dipoles in this case, which point towards oxygen, do not cancel out because it's a bent arrangement. Another helpful rule related to this, which comes into play with some of these structures that have one lone pair, is that all bent molecules are polar. All right, so we talked about last time, if you have 3 atoms in your whole formula, it's either going to be linear or bent. Those are your only 2 options. Bent molecules are polar, and this is an example of one of those, but anytime it's bent, it's going to be polar. So again, the key here is to recognize patterns. That's always helpful in approaching problems like this. And then the last category I'll talk about is the one that's a little bit more complicated, and I'll have a summary on the next slide that kind of goes through all the possibilities, so we're not going to have to talk about all the different things here. If the structure has more than one lone pair, there's not really a hard and fast rule you can say. It, may or may not be polar. I know that's an unsatisfying header for a page in your notes, but the reality is if you have more than one lone pair in the structure, some of them are polar, some of them are not, and you have to think about, again, whether or not the dipoles cancel out. And I'll give a chart on the next page that kind of summarizes all these, but as you'll see the different possibilities. And here's just a couple of them here. So if we give a couple examples down here, if we do water, as we said, I already mentioned, is a polar molecule. So water is AX2E2, so we have the 2 lone pairs on oxygen as well. But again, following the rule that I gave you last time, this is a bent molecule, and so it will be polar. Any bent molecule is polar, whether it's 1 lone pair or 2. So that's an example of a polar molecule that has more than 1 lone pair. But then if we talked about this structure last time, xenon difluoride. Actually, that's a good one to do. Let's do xenon tetrafluoride, a little bit better. All right, so if we do xenon tetrafluoride, this one was one of the only ones we saw last time that was square planar. So it's 6 electron groups, octahedral arrangement, and then we have fluorines arranging themselves in a square plane. If we draw it this way, it's a little bit more obvious to see why this one would end up being nonpolar. So if we draw it with all the atoms in the plane, we have dipoles pointing towards fluorine in every case, but we have those 2 that are horizontally oriented canceling each other out, and then these 2, which are vertical, pointing up and down, also cancel each other out. So they cancel each other out in both directions in this time. We talk about the linear molecule where they cancel out in one direction. For a square planar molecule, which is AX4E2, you have that cancellation happening in both directions, vertical and horizontal, as I've drawn it here. So this would be nonpolar. So for structures that have 2 or 3 lone pairs, we see some with 3 as well, then there's multiple possibilities. So you have to think about it a little bit more in depth. You can't just come up with a simple rule for those ones. But what will be helpful for you, I think, as you go through this is I have a summary later on. I guess I didn't put it right here, but there's this summary here that I'll come to a little bit. So That'll kind of summarize all the different possibilities. Let's just go through a couple of real examples and just decide if it's polar or nonpolar. And as I said, the majority of the ones you're going to have to do and deal with on the homework assignments and exams are going to be, the simple A, X, M, E, whatever structures, where you have a center atom, one type of outer atom, and you just need to predict if it's polar or nonpolar. So there's some that are a little bit more complicated, but in general, you're going to mostly be doing this. You have questions? Sorry.
What's the shape of like the XCF4 again?
It's called square planar, so I should write that out. So in this case, the 4 atoms are oriented at 90-degree angles around the center atom, exactly in a square. So that's how it works for that one. That's not the most common geometry, but it does exist for this molecule. Anything else before I move on? Okay, so then let's do a couple examples just to see how this will work. So if we have PCL5, all of this starts with a Lewis structure. So we covered Lewis structures in the last chapter, and I mentioned it would be important not only for chapter 3, but a lot of the stuff we do in chapter 4 as well. So this starts with a good Lewis structure. At least for this one, I'll go through all the steps with you just to make sure you remember them. So PCL5, we have 2 elements, phosphorus and chlorine. Let's take a quick look at the periodic table. Where do I have that? All right, this one. All right, so if we find the periodic table, we have to figure out valence electrons. That's the first step. All right, so it's PCl5. Phosphorus is here in group 5, so 5 valence electrons. Chlorine is here in group 7, so it's going to have 7 valence electrons. So that's the valence electrons for each atom. We have 1 phosphorus. So there's 5 electrons for phosphorus. 5 chlorines in the formula, 7 each. So that's going to be a 40 electron structure, 40 valence electron structure. So when we draw this, we start with single bonds to all the outer atoms. We complete the octets of the outer atoms by adding 3 lone pairs to each, a total of 6 more electrons to each one, to give them each a total of 8. And now what we take stock of is how many electrons we've used. So we've completed 5 octets, 1 for each chlorine. That's 5 times 8 is 40. That's all 40 of our valence electrons. This one will not have any lone pairs on the central atom. And for VSEPR and polarity, the 2 topics we're covering in this chapter, again, we don't need to really worry about formal charges or double bonds. This one doesn't have any double bonds or formal charges, as it turns out. But we don't even really need to think about that. So this is fine. We just need to know how many lone pairs are on the central atom. So this is AX5E0, or more simply AX5. If you want to talk about the shape of that molecule, it's trigonal bipyramidal. But whether you remember the name of the shape or not at this point, we talked about earlier that if it has no lone pairs on the central atom, all the x's are the same. If both of those are true, then it's going to be nonpolar. All right, so you want to get, again, pretty proficient at drawing Lewis structures, because you need to be able to quickly identify the sort of AXE category that the molecule falls into, both to be able to predict what its shape is if we ask you about that, or to be able to predict its polarity. That's often the most straightforward way to get to that. So anything that has no lone pairs on the central atom and only 1 outer atom, in this case chlorine, will be nonpolar. So this is an example of that. All right, any questions on that? All right, and then just one more that's an almost identical problem, just a different molecule. We want to do it for IF3. So if we do IF3 in this case, I'll go through this one a little bit more quickly. So the Lewis structure you should get for IF3 I'm drawing it in a suggestive way already, but so that's going to be, so IF3 has 28 valence electrons, so that's 24, and then you're going to still be left with 2 lone pairs on the central atom. So IF3 is AX3E2, and as we said, for structures that have 2 lone pairs or 3 lone pairs, there's not a simple rule for whether or not they're polar or not. So we actually need to think about the structure of this molecule. So I've already sort of drawn it correctly just to save myself some time of having to redraw it. This is a T-shaped molecule. So you have, again, that's the T shape as we talked about. So in a T-shaped molecule, you have two dipoles that are more or less opposite of each other. So those two would pretty much cancel out. One points up, one points down. But we have the third left to right dipole between iodine and fluorine that will not be canceled out because there's no other fluorine atoms on the other side. So this molecule would have a net dipole left to right as I've drawn it, because the dipole moment for this IF bond that's drawn horizontally does not cancel out with anything. These two cancel each other out more or less. They're not perfectly linear in this case, but they're close. But this dipole moment here is going to be not opposed by any other one, so you'll have a net polarity from left to right, so this molecule would be polar. And that would be true for any AX3E2 molecule. They would all be polar. So you don't, again, that's another one that across the board, whatever the formula is, if it comes out to AX3E2 category, that would be polar. You can memorize that if you want. I again encourage you to think about the shapes and sort of think about the, how the dipoles arrange themselves around the central atom and whether or not they cancel out. I don't want you to be too, robotic with this, but if you just want to remember that that's the case, that's going to be true for any AX3E2 molecule. All right, so here's sort of the key summary table. This table here summarizes both VSEPR, which we talked about last time, and molecular polarity. And again, this is going to be true for the situations where all the X's are the same around the central atom. So if you have more than one type of outer atom, you do need to think about whether those cancel each other out or not. But in cases where all X's are the same, you can use the AXE notation, the category that they fall into, to predict polar or nonpolar. And as we see here for the structures over here that have more than one lone pair, two of them are nonpolar, two of them are polar. So as I said, both possibilities are there. So do we have questions on molecular polarity before we move on from this? Yes?
So what do the A, X, E stand for?
So A is the central atom,
Yes.
X is an atom that's bonded to the central atom, and then E is the lone pair. So the subscripts tell you how many of each of those you have. So the number of X is the number of atoms bonded to the central atom, and then E is the number of lone pairs on the central atom.
X is how much active bond, right?
Yes.
And E is lone pair.
Yes, exactly.
E is like the lone pairs of the central atom.
Yes, exactly. Yep. So all this is from the perspective of the central atom. The outer atom lone pairs don't particularly factor in when we're making predictions about shapes or polarity. Okay, any other questions before I leave this topic? All right, so then what we're going to do next is this is still going to be sort of related to molecular geometry, but we're going to start talking about how exactly are covalent bonds formed. So at this point we have the idea in our head that a covalent bond is two shared electrons, but how are the electrons shared? What do the orbitals look like? How do we get these different shapes when we form covalent bonds? All those are going to be sort of covered in this next part of the chapter. So the first approach we're going to talk about to sort of rationalize covalent bonding and talk about how it works in more detail is called valence bond theory. So you might see this terminology in the homework assignment. Valence bond theory. So there's going to be two bonding theories we cover. The first one is called valence bond theory. And what this one sort of assumes is that we have orbitals on each atom. So if two atoms are bonded to each other, we have an orbital on the first atom, an orbital on the second atom, and those two orbitals overlap with each other. And the two shared electrons are going to be in that region that's overlapping between the two atoms. So you still have an orbital on one atom and an orbital on the other. Each atom still has its own orbital, and it's the overlap of those two orbitals that allows the electrons to be shared. So that's what valence bond theory is. It's a very localized approach. It again assumes that each atom has an orbital and that the electrons are shared in the region between the two atoms where those orbitals overlap. So it's a very localized approach to bonding in molecules. But it works pretty well for a lot of simple molecules, and it's a bond theory that's still very popular in organic chemistry. So if you take, I guess you guys call it orgo here. I called it OChem when I was in college. But when you take that course, if you do, you'll see valence bond theory a lot, and the terminology from that will be very, very commonly used. So for some simple molecules, the orbitals that overlap to form the covalent bond can just be simple atomic orbitals. We don't have to do anything more complicated than that. So if we make the simplest molecule H2, we're going to take two hydrogen atoms. So you'll recall hydrogen is the first element on the periodic table, so its electron configuration is 1s1. So each hydrogen is going to have a 1s orbital, a spherical orbital with a single electron in it. So we take one hydrogen atom, we combine it with another hydrogen atom that has also the same electron configuration, a single electron in a 1s orbital. And so what we do is we take these two 1s orbitals and we overlap them with each other. And that's going to make H2. So if we put the nuclei, there'd be like a nucleus here and here, for example. But that's going to make H2, where we have two overlapping 1s orbitals. And the two shared electrons are going to be in that part of the orbital, or they're going to mostly be in the part of the orbital that are overlap with each other. So again, the shared electrons that form the covalent bond reside in that overlap region. So that's how we can do it for a simple molecule like H2. Just take the two 1s orbitals and overlap them. And even for things that involve other types of orbitals beyond s orbitals, in many cases we can just invoke two atomic orbitals overlapping to make a bond. So if we have Cl2, each chlorine atom has a valence electron configuration. So I guess the full configuration would be neon, and then we'd have 3s2, 3p5. So again, reviewing electron configurations. That's the electron configuration for chlorine. In this case, we cannot use the s orbitals to overlap and form a bond because each s orbital already is doubly occupied. So we can't put two of those together because we can still only put two electrons per orbital. So because the 3s orbital is filled here, instead the bond would form using the unpaired 3p electron. Okay? Because in a 3p5 configuration, you have one unpaired 3p electron, and so two unpaired electrons, one from each chlorine atom, you can have the orbitals overlap, and then those two electrons can become shared. So what that would look like in a pictorial format is, remember p orbitals have these sort of figure 8 or dumbbell shapes. So you have a 3p orbital on one chlorine atom that has an unpaired electron in it. You have a 3p orbital from another chlorine atom that has an unpaired electron in it. And I'm going to draw the product a little bit bigger just so you can see it better. But basically these two 3p orbitals in the places where the orbitals have the same phase are going to overlap with each other, and those two unpaired electrons are going to be then shared in that overlap region. So this will look something like this. It's not the easiest to draw for someone who's artistically challenged like me, but you'll get an overlap there of the two 3p orbitals. So each one has a 3p orbital. The orbitals overlap, and the two electrons are going to primarily be in that overlap region holding the two atoms together in Cl2. All right, so that's another example of using, I didn't shade that one very well, of using atomic orbital overlap to describe how a covalent bond would be formed between two atoms. And then finally, if we go to a slightly more complicated example, HCl, we're going to sort of combine the two things we've used here. So in this case, we have two different atoms with two different valence electron configurations, 1s1 for hydrogen, and then as we said, for chlorine, it's 3s2, 3p5. So it's also possible to use two different orbitals overlapping to make a covalent bond. So we're still going to have a 1s orbital from hydrogen, and then for chlorine, the unpaired electron is still in a 3p orbital. And those can combine with each other, where now two different orbitals, a 1s and a 3p, overlap, and then the shared electrons go in that region that's overlap between them. So you would have your 1s orbital. Oh man, I didn't draw that very well at all. And then your 3p orbital. So again, a 1s orbital from hydrogen, a 3p orbital from chlorine, and two shared electrons in the place where those two orbitals overlap with each other. All right, so that's, again, this is hydrogen on this side, chlorine on that side. And you overlap two atomic orbitals where they initially had unpaired electrons in them, and then the overlap of those orbitals allows those two unpaired electrons to be shared. So that's kind of how valence bond theory works. And those are the simplest cases, though, where it's just two atoms bonded together, and we can just use atomic orbitals from those two atoms to make that bond. But now we need to talk about what happens in more complicated cases where you have more than two atoms, and you can't just necessarily use straight-up atomic orbitals. So let's talk about the first case. And so now we're going to introduce the concept called hybridization, which often is going to be necessary to consider when we're talking about covalent bonding in other molecules. So if we do BeCl2 here, technically beryllium's a metal, but we still can sort of draw it using the same, Lewis structure approach and then using VSEPR to predict its shape. So BeCl2, what we would predict is AX2 linear geometry. So that's the geometry we predict from VSEPR, and that is in fact correct. But if we think about the electron configuration of these atoms now, the central atom here is beryllium, and we're going to arrange the orbitals from low energy to high energy, so that's the vertical scale here. And if we go to the periodic table, we can figure out that beryllium has an electron configuration of helium and then 2s2. All right, so the electron configuration of beryllium, the valence electrons are 2s1, 2s2. So in a beryllium atom, this is what it would look like. And in essence, we cannot easily suggest how we're going to use atomic orbitals to make these bonds. Because again, BeCl2, we're going to need to make a linear molecule with a bond to one chlorine on one side, a bond to the other chlorine on the other side. How do we do that if we just have two paired electrons in a 2s orbital? We don't have any unpaired electrons that we can overlap with the chlorine 3p, and the 2s orbital is spherical shape, so how do we get a linear geometry like this? So what happens in this case is we do what's called hybridization. So essentially we mix, sorry, I think this is blinking a lot, I can't even tell because it's behind me, but I taught in another classroom the other day and it was fine, so I think it's the HDMI cable in here. I'll suggest that to them. All right, anyway, we hybridize a 2s orbital and a 2p orbital on beryllium. What it means to hybridize them is to take two different orbitals, in this case 1s and 1p, and we're going to mix them together to make new orbitals that are sort of a blend between s and p. So they're no longer pure atomic orbitals. They're a new type of orbital called a hybrid orbital that's a mixture of s and p orbitals. It looks kind of like in between the two. That's how it looks like, and it's also its energy is in between. So what we get then are, if we mix one s orbital and one p orbital, we take two orbitals and blend them together, we get two hybrid orbitals that are called sp hybrids because we've mixed one of each together. And then we still have two other 2p orbitals that were not mixed, so those are going to still remain as pure 2p orbitals. So then what happens is when we blend the two orbitals together like this, we have two unpaired electrons that can then overlap with the unpaired electrons in chlorine to make the two bonds. That's how hybridization works. So these hybrid orbitals, their energy is in between s and p, but they're now degenerate with each other. So when we fill these with the electrons, we're going to put one electron into each following Hund's rule, and that now gives us two unpaired electrons that can overlap with chlorine to make the two bonds. And then these two orbitals here, which remain empty, these are just unhybridized 2p orbitals where their energy is unchanged. They're going to still be just pure 2p orbitals, but they're going to remain empty in this case. All right, and these sp orbitals are going to be arranged linear to one another. So there's two sp orbitals and they're pointing in opposite directions, and so that gives us a linear geometry. So this hybridization is sort of also how we can rationalize the different molecular shapes we can make, where when we hybridize orbitals, if we're going to make a linear molecule, we hybridize two orbitals, we get an sp hybrid set, and that set of orbitals is one sp orbital pointing one way, one sp orbital pointing the opposite way, each with an unpaired electron that can then go and form a bond. So that's what hybridization refers to. It's a mixing of two atomic orbitals. And it's kind of an abstract concept, admittedly, but it's how we can sort of, again, justify the ability to form these different shapes and to make these different types of covalent bonding arrangements when in the free atom we don't have any unpaired electrons in the correct orbitals. All right, so let's do another example of, we're going to talk about, there's like five types of hybridization. Three of them we'll kind of go through. And again, these sort of pictures that I'm drawing here, sort of, what's happening with hybridization, why it happens, it's helpful for you guys to understand that. I don't want to say that this isn't important, but as we'll see when you do homework assignments and tests, mainly what you're going to be able to have to do, which is often very straightforward, as I'll show you, is just predict the hybridization. So you'll be given a molecule, you'll say, what's the hybridization of the central atom? And you'll just say what that is. But here we're going to go through a little bit deliberately of how hybridization works, why it happens, and hopefully that'll kind of help you sort of visualize what's going on even though the way that we'll examine you is not going to usually go into those levels of detail. Yeah. So we say, can we predict hybridization by the Lewis dot structure? Is that what you asked? Okay, sorry, I'm having a hard time hearing you from up here. But yes, so as we'll see, it all is related to the Lewis dot structure. So that AXE notation that we've been talking about that relates to both the shape and now the polarity also factors directly into the hybridization as well. So we'll get a summary of that a little bit later on, and you'll see how there's a direct correlation between those and how it's very simple to predict once you have a correct Lewis structure drawn for that molecule. So they are all related still. Okay, so for sp2 hybridization, this is going to be a situation when you have 3 electron groups, the trigonal planar electron group arrangement. All right, and so an example is BF3 that we're going to talk about here. So our central atom is boron, which has valence, again, 2s and 2p orbitals. And if we think about the electron configuration from boron, that's just 1 over from beryllium in the periodic table. So beryllium we saw last time was 2s2, and boron is going to be 2s2, 2p1, 1 more electron to get you to boron. And again, if we look at this picture here, it's not clear how would this central atom boron make 3 identical bonds, because 2 of its electrons are paired, they're in 2 different orbitals, and then the arrangement of those orbitals is not trigonal planar. You have a spherical s orbital at the middle, then you have your p orbitals that point at 90-degree angles. So how does any of that make sense if you're trying to make a trigonal planar molecule with 3 bonds? And so what you have to do again is you have to hybridize some of the s orbital with some of the p orbitals. So in this case, we're trying to form 3 identical bonds to make a trigonal planar molecule, so we need to hybridize 3 orbitals. So we hybridize one of the s orbital always with, in this case, 2 of the p orbitals. So we're going to mix 3 orbitals together this time. So that's again called hybridization, where we mix orbitals, atomic orbitals, to make new hybrid orbitals. So we're going to mix 2s and 2p. We're going to take, in this case, 2 2p orbitals to mix a total of 3 orbitals. And we're going to make a set of what's called sp2 hybrid orbitals. So again, because we've mixed an s orbital and 2 p orbitals, we call them sp2 hybrids. 3 identical sp2 hybrid orbitals, which again are a blend between a 2s orbital and a 2p orbital, not one or the other, but a mixture of the 2. And when we do this, we have 3 valence electrons on boron that are going to distribute evenly in those 3 orbitals to obey Hund's rule, and then those can then overlap with the fluorine atomic orbitals to make the 3 covalent bonds. So again, each fluorine has unpaired electrons as well, so they overlap with these 3 to make the 3 bonds. And so with 3 hybrid orbitals, we can make 3 bonds. And again, the arrangement of the sp2 hybrid orbitals, you know, again, it's mathematically complicated to come up with why this is, but when you have sp2 hybrid orbitals, there are 3 identical orbitals that are arranged in a trigonal planar fashion. So you have 3 orbitals all in the plane, 120 degrees apart, and then you just still have this empty 2p orbital, which in the case of BF3 remains empty. No electrons will be in that 2p orbital, or no bonds will be involved with that one. Okay, so that's sp2 hybridization, where we have to mix 3 orbitals together to get the 3 identical hybrids that can form the bonds. And then the same pattern for sp3. So this is going to start to hopefully look a little bit routine at this point, where if we have sp3 hybridization, this is going to be 4 electron groups on the central atom, or a steric number of 4 as I defined it last time, and that's a tetrahedral geometry, if you remember. All right, and so the classic example of this is methane CH4. Okay? And another important thing to remember is that the bond angle for tetrahedral, remember, it's not the most intuitive number, but it's 109.5 degrees. So that'll factor into our discussion a little bit as well. Okay, so we have 2s and 2p orbitals. This is our energy scale again. So in the free carbon atom, when carbon is by itself, not bonded to anything, we know that the valence electron configuration for carbon is 2s2 and then it's 2p2, which is, again, 1 more over from boron now, so make it 2s2, 2p2. And looking at this arrangement of electrons, it should again be puzzling, how can this molecule form 4 bonds? It only has 2 unpaired electrons, first of all, and the 2 unpaired electrons are in 2p orbitals. Now, as you'll remember from chapter 2, if we have 2p orbitals what are the sort of orientations of those 2p orbitals? We call them 2px, 2py, 2pz, meaning they're oriented in the x, y, and z directions. And so what's the angle between a set of 2p orbitals? Or what's the angle between the x, y, and z coordinates? 90? Yeah, don't think about it too hard. So if you have an x, y, and z coordinate, I'll just draw the two-dimensional ones. Remember, the coordinates are all 90 degrees apart from each other. So if you have just 2p atomic orbitals, they're going to be 90 degrees apart. So if you just use those 2p orbitals to make bonds, your bond angles would have to be 90 degrees. But here they're 109.5, quite a bit different than 90. And so the only way to sort of justify and rationalize that is, again, to hybridize the orbitals. So if we want to make 4 identical bonds in this case, we're going to hybridize our 2s orbital with all 3 of the 2p orbitals. We're going to hybridize a total of 4 orbitals to make our 4 identical bonds. So this time we're going to use all 3 of our 2p orbitals and make a set of what are called SP3 hybrids. So in this case, because we've used all 4 of our orbitals, 2s and all 3 2p orbitals, we form a set of 4 orbitals, and there's no more unhybridized orbitals left. We've hybridized all of our atomic orbitals to make an SP3 set. And so in the SP3 orbitals, we have 4 electrons, 4 degenerate orbitals, so they're going to go, again, 1 in each orbital, and that's going to give us 4 identical bonds when they overlap with the 1s orbitals from hydrogen, and 109.5 degree angles between all of those hybrid orbitals. So when you make a tetrahedral arrangement of electron groups, then it's going to be SP3 hybridization to get those 4 orbitals arranged 109.5 degrees apart. So that's the 3 of the 5 cases for hybridization. So what we're going to have to be able to do in this course is predict hybridization. That's mostly what we're going to ask you for when we do problems like this, is what is the hybridization of the central atom in this molecule, or we'll give you a more complicated atom or molecule and say, what's the hybridization of that specific atom? And it all is directly related to that term we talked about last time called steric number, which is the total number of electron groups. Where an electron group is either a bonded atom on the central atom or a lone pair. All right, so if you know the steric number or the total number of electron groups on your central atom, which you will have once you draw the Lewis structure, then you can very easily predict the hybridization. So the orbitals that are going to be available to hybridize, as we've already shown, you can hybridize an s orbital. You'll have 3 p atomic orbitals to hybridize. And then in some cases, we also invoke hybridization of d orbitals. So remember that there's 5 d orbitals as well available. In reality, we only ever use up to 2 d orbitals. So we're not going to use all 5, but we have d orbitals as well in some cases. When we have a steric number that's greater than 4, we invoke that. Okay? All right, so then if we look at a steric number of 2, we need to hybridize 2 orbitals. So we pick the first 2, s and p. And that gives us SP hybridization. So if your steric number is 2, you hybridize the first 2, S and P. That gives you SP hybridization. And that corresponds to the geometry that we would predict from VSEPR, which is linear. Okay? As we saw, when we have a steric number of 3, AX3 or AX2E, or whatever combination we have that's 3 electron groups, we need to hybridize 3 orbitals. So we go S and then 2p, total of 3 orbitals to hybridize for a steric number of 3. So we have 1s, 2p, so that means the hybridization is called SP2. It's not called SP squared, it's called SP2, so that's just the way we describe it. And that corresponds to the trigonal planar geometry. All right, so there's nothing new about the geometry here. The hybridization that we predict gives exactly the geometry that we would also predict from the VSEPR approach. So there's a perfect correlation between those. And if we have a steric number of 4, we need 4 orbitals hybridized. So that's going to be an s orbital and all 3 of the p orbitals for a total of 4, which we call SP3. And that gives us a tetrahedral geometry. Now the 2 that we haven't talked about yet are steric numbers of 5 and 6. So if we want to have 5 electron groups, we can't just use s and p orbitals because there's only 4 of those total, so we have to start hybridizing other orbitals, which we would say is the d orbitals. So for 5 electron groups, we need to hybridize 5 orbitals, so it's going to be s, 3p, and then 1 d orbital for a total of 5 orbitals. So those 5 orbitals we need to hybridize, and we call that SP3D hybridization, indicating that 1 d orbital is also involved in the hybridization. And that gives us the trigonal bipyramidal geometry. And then the highest steric number that we can possibly have, as we talked about last time, is 6. 6 electron groups around the central atom, which is octahedral in terms of the electron group arrangement. And in that case, we need 6 orbitals. So S and 3p is 4, and then we need 2 d orbitals in this case to get a total of 6 hybrid orbitals, SP3D2. You might see these written sometimes as DSP3 or D2SP3. Doesn't really matter what order they're put in, but that's the total hybridization we would have, which is octahedral. Now I feel a little bit bad at this point because I have what they would call a thin face. I don't like lying to people. And when I teach you guys hybridization, I am lying a little bit. So in reality, the d orbitals are not very much involved in bonding for, for main group compounds like the, ones we're talking about in this course in the p block. In transition metals, d orbitals are very important, but we call it SP3D hybridization, we call it SP3D2. The reality of the situation is that the d orbitals are not very strongly involved. We're kind of lying to you when we say that. Now, it's not necessarily a bad lie because there's, remember that the valence bond theory and hybridization is sort of a model for covalent bonding. And, a model is kind of like a theory. We define that early on in the course. But another definition of model that I've heard, which I've liked, is that a model is a lie that is designed to help us understand the truth. So in some sense, hybridization, especially the ones that involve d orbitals, is a bit of a lie. It's not really the true story of what's happening, but it helps us rationalize things. It helps us kind of understand things a little bit better, and so we still use it in many contexts, even though, again, from a physical standpoint, it's not 100% correct. We're going to learn in the next class the more correct and more sort of rigorous bonding theory, which is called molecular orbital theory. That one works really well, but is also excessively complicated for anything that's not just 2 atoms bonded together. So, this is a nice bonding theory because even though it's not always physically correct 100%, we can use it for a wide range of molecules, and it does help us rationalize some important things about their bonding. And especially in organic compounds like you'll see in that course, then this sort of hybridization approach is very common and very useful. All right, so any questions on predicting hybridization before I do a couple examples? All right, so let's work through a couple examples of this. Predict the hybridization of the central atom in COCl2. Sorry, I'm all out of order here. All right, so for COCl2, when we're predicting hybridization, the first thing we need is a good Lewis structure, at least one that's relatively close to being correct. So for COCl2, I'm going to not go through all the details because we've reviewed this many times already, but again, work this one out on your own if you still want to practice more with Lewis structures. And so what we get for COCl2 is this. And technically speaking, we do need a double bond between carbon and oxygen to make sure that we complete the octet on carbon. It turns out for just predicting the hybridization, if you forget to do that, you're going to get the same answer because it's all determined by the steric number of your central atom, which is not determined by whether it's singly or doubly bonded, just how many things are bonded to the central atom. So in this case, this would be an AX3 structure, 3 total electron groups, or a steric number of 3. And so if it's a steric number of 3, we have an s orbital and 3 p orbitals available for hybridization, and we would need to hybridize 3 of those orbitals to make 3 identical bonds around that. They're not identical in this case, but to have 3 bonds in a trigonal planar fashion, you need sp2 hybridization. All right, so that's how we predict hybridization for a simple molecule like that. You just, again, draw the Lewis structure, figure out how many electron groups are around the central atom. So you do need to make sure you know if there's any lone pairs or not, because that factors in as well. Those all count as electron groups. But then once you know the number of electron groups, you just hybridize that many orbitals, and that gives you the hybridization of that central atom. Yes, question in the back? Yes, so SP3D2 would be the highest that you will go. And that's because, as we talked about, we don't have any geometries that have more than 6 electron groups. So that's the highest we'll see. In some, compounds that involve metals, like the transition metals or those F elements, the actinide and lanthanide way at the bottom, you can have more than 6 things bonded to that, but in that case, the bonding theory is like totally different, so you wouldn't use hybridization anyway. So for hybridization, that's as high as it'll go, SP3D2. Any other questions? All right, the next, oh, sorry. So the number of electron groups is the number of atoms bonded to the center atom plus the number of lone pairs on the center atom. So our carbon is bonded to 2 chlorines and 1 oxygen. That's 3 things that it's bonded to, has no lone pairs, so the total is 3. So that's where that number comes from. All right, the next one we're going to do is also useful for exam 1 because we might give you, I didn't cover these in class yet, so I guess now is as good a time as any. We might give you a problem like this where we ask you to complete a more complicated Lewis structure using what's called a skeleton structure. So we'll give you what's called a skeleton structure where we draw how all the atoms are connected to each other, but we draw all single bonds with no lone pair shown or no multiple bonds shown. And you have to first complete the Lewis structure before you can then answer the question about how many lone pairs there are, how many double bonds there are, what's the hybridization as we're doing here, and so on. So you have to be able to complete the Lewis structure first. So this looks very complicated, so we're going to go through this in a little bit of deliberation just to make sure we know how to approach this. So when you're doing structures like this, you know, the approach that I covered for Lewis structures where you count valence electrons, distribute them, complete the octets, follow the formal charges, all that, it gets a little bit cumbersome when you have this many atoms in your formula. So for these types of problems, what we want to do is we want to recognize some patterns in terms of how these different sort of 2p elements, these are mostly going to involve, you know, carbon, oxygen, nitrogen, and then also hydrogen as we show here. How do these different atoms tend to have their valence electrons arranged to complete their octet and to avoid formal charges? So just recognizing the patterns for that, not having to go through it in as much detail as we would for a simpler molecule. So in these types of compounds, we're going to have primarily hydrogen, and then carbon, nitrogen, oxygen, or sometimes halogen atoms, which would be fluorine, chlorine, etc. So for these types, these are what we would call organic compounds. So when you talk about organic chemistry, these are the types of compounds you're dealing with. And if we're going to complete the Lewis structure for one of these, we can look at sort of the typical arrangement of valence electrons for all these different atoms that are going to likely be in the structures. So we've already talked about hydrogen at length. Hydrogen will form 1 bond. So in problems like this, you shouldn't do anything else to hydrogen because it's already going to be shown with a single bond. It's never going to have double bonds. It's never going to have lone pairs. As I said, I get very upset when I see that, so don't do it. For the rest of these, though, there's going to be patterns. Now, all these other atoms, carbon, nitrogen, oxygen, or the halogens, they're going to want to have a complete octet, total of 8 electrons around them. And to minimize formal charge, though, those 8 valence electrons are going to be following different patterns. So for carbon, you tend to have 4 bonds, and that's going to give you those 8 valence electrons total. So you'll have 4 bonds to carbon. Nitrogen will tend to have 3 bonds and 1 lone pair. So that's a total of 8 still, but now it's 3 bonds and 1 lone pair for that total of 8. Oxygen is 2 of each, 2 bonds and 2 lone pairs. And you may have already started to notice some of these patterns as you went through and practiced formal charge examples, where these are the arrangements of valence electrons in those atoms that are going to give you 0 formal charge, which is ideally what we want. And then for the halogen, you're going to have 1 bond and 3 lone pairs. So all of these, again, have a total of 8 valence electrons, just different combinations of bonding pairs and non-bonding pairs to give you that total of 8. All right, so that's how we're going to do it for all these different atoms, and these are the ones you're going to typically see. There will be rare cases where these rules aren't followed, but again, make sure you're following the octet rule first and foremost. Make sure everything has 8 electrons around it. If you can't get all these quite right, but in 99% of cases, it will follow this approach. So to go through and complete the Lewis structure of this molecule, we're just going to work through all the different atoms in the structure and see what we need to do to get them to follow these patterns here. So carbon should have 4 bonds. If we look at this first carbon atom here, it already has 1, 2, 3, 4 bonds, 4 single bonds. So that one we're not going to do anything to. We don't want to add any more. We're going to go beyond an octet. The second carbon atom, though, right now only has 3 bonds, and does the third one as well. Both of these 2 carbon atoms have 3 bonds. So to make sure they both have 4 bonds and no lone pairs for carbon, I'll write that out explicitly, 0 lone pairs for carbon, to complete their octet, we can do that with a double bond there. So by putting a double bond between those two carbon atoms, now each of them has exactly 4 bonds. And they're all happy now. We go to the next carbon in the molecule. This already has 4 bonds. Again, 4 single bonds. So we're not going to do anything to this carbon here because it already has its 4 bonds. But then for the rest of this, we're going to have a little bit of things we're going to need to fix. So for this carbon here, we have 3 bonds right now. It wants to have 4. This oxygen only has 1 bond and 0 lone pairs. So the way that we can satisfy both of those is by drawing a double bond. So by doing this, this carbon atom has 4 bonds. This oxygen has 2 bonds. And we're going to fill it in with the 2 lone pairs. All right, so oxygen is not bonded to anything else, so it needs to be a double bond to carbon to make sure that that oxygen has a total of 2 bonds. So this carbon is now fine. It has 4 bonds. This oxygen is fine. It has 2 bonds and 2 lone pairs. And then we have these 2 carbon atoms here. Right now, each of them has 2 bonds. This one to the 2 carbons next to it. This one to a carbon and a hydrogen. Each carbon wants to have 4 bonds, so we need to add 2 more to those 2 carbon atoms, and we can do that by drawing a triple bond between them. All right, so now each carbon has 4 bonds, a triple bond between the 2, and then an additional bond on either side. All right, so again, that's going to take some practice for you to get used to that approach, but if you follow these patterns and kind of internalize them, that'll help you quickly put together these Lewis structures without having to go through too much effort to get all the multiple bonds and lone pairs worked out. So then from there, we can now go through and predict the hybridization of all the carbon atoms in this molecule. So we have that carbon atom there, that one there, that one, that one, that one. Hopefully I gave myself enough room. So we have 1, 2, 3, 4, 5, 6, 7 carbon atoms in the molecule. We're going to predict the hybridization for all 7 of those. And that's going to again come just from counting the number of electron groups that are bonded to each carbon. How many things is it bonded to, including any lone pairs, which the carbon won't have. So this first one here is bonded to 4 things. 3 hydrogens and a carbon, so 4 bonds makes it SP3 hybridization. The second carbon here is bonded to 3 things. It has 1 double bond, so it has a total of 3 things bonded to it, 2 carbons and a hydrogen, so 3 things is SP2. This one also has 3 things bonded to it, 2 carbons and a hydrogen, so that one's also SP2. This central carbon here in the middle also has 4 bonds, 4 single bonds. So for 4 single bonds, it needs to be SP3, just like the first one. This one that's doubly bonded to oxygen has 1, 2, 3 electron groups bonded to it, one of them being double bonded again, so it's going to be SP2. And then these last 2 carbons here, each of them are only bonded to 2 things, 1 carbon on each side for this one, a carbon and a hydrogen for this one. So both of these have 2 electron groups attached to them, which makes the hybridization now SP. So we have all different possibilities for hybridization in this molecule, SP, SP2, SP3, for all the different carbon atoms. And once you fill in the structure, it becomes fairly simple to do that and count the number of electron groups and then get the hybridization. All right, now for this problem here, you probably didn't need to put in all the double bonds because that doesn't change how many things each one is bonded to. But for completeness, you should, and there might be other questions where it's important that you do account for how many double bonds there are in the structure, how many lone pairs, and so on. All right, so any questions on this one? All right, it's a new thing you saw, so make sure you practice this because there could be a couple exam questions that ask you to do this. Again, it's a question bank, so you might not see it at all, but just be ready for it. All right, the last thing we're going to cover with whatever remaining time we have today is the different types of bonds we have. So we've talked about how, okay, we're going to, on the central atom or on any atom in the molecule, we can hybridize the s and p orbitals, make these sp hybrid orbitals, and form these covalent bonds. But again, there's still some missing details in terms of how exactly are those hybrid orbitals involved in bonding, and sort of what do the bonds themselves look like. So there's going to be 2 types of bonds that are going to be formed in these types of structures. So the first one is called a sigma bond. So we're going to have to, again, expand our Greek alphabet for this part of the course. So sigma bonds are going to be bonds that are formed by end-to-end overlap of atomic or hybrid orbitals. Now the bonds that I sort of drew at the very beginning of this, where I showed 2 overlapping orbitals, those are essentially sigma bonds that I already drew. So you kind of already know what these look like from earlier. But we'll formalize the definition here. It's called by end-to-end overlap of atomic or hybrid orbitals. And another more formal definition of this is that the electron density is greatest in between the nuclei along the direction of the bond. All right, and so again, sigma bonds form when you have two orbitals that are overlapping in between the two nuclei, and that gives you the greatest electron density right in that overlap region. Kind of like we already drew earlier today. So that's one type of bond. So everything we've seen so far will be sigma bonds. All right, so the electron density is in between. So if you can see me from wherever you are in the room, you have two orbitals coming straight at each other. They overlap right in the middle, and that overlap region has those shared electrons, and that would be called a sigma bond, that sort of head-to-head overlap of two orbitals. So what type of orbitals are involved in sigma bonds? They're going to be, as I said, they could be atomic orbitals. That's what we talked about at the very beginning of this, but they can also be hybrid orbitals. So they're atomic and or hybrid orbitals. And an important thing to recognize at this point is that if you have hybrid orbitals involved, so if your central atom or other atoms in a more complicated structure, if they're hybridized, those hybrid orbitals can only form sigma bonds. So there's two types of bonds we're going to talk about, sigma, the next one is pi. Hybrid orbitals can only form sigma bonds, or they can hold the lone pairs. So we haven't seen examples explicitly in this section that involve lone pairs, but if your central atom has lone pairs, the lone pairs will also be in hybrid orbitals. And then any sigma bonds you have will also involve those hybrid orbitals. That's what hybrid orbitals do. They form sigma bonds, which are sort of those head-to-head overlap types of bonds, or they would have lone pairs in them if they're not if they involve non-bonding electrons. So that's what the hybrid orbitals do, and that's what a sigma bond would be defined as. Now the other type is called pi bond. We haven't really seen this yet. So a pi bond is a side-to-side overlap of two atomic orbitals. And so what this results in is you have regions of electron density that are greatest above and below the bond axis. That'll make more sense when I draw a picture of it here in a second. And in order to form pi bonds, there's only one type of orbital that can do this. It has to be an unhybridized p orbital. So as we talked about, when you have hybridization that's anything less than sp3, so if you have sp or sp2 hybridization, you're going to leave one or two p orbitals unhybridized, and those unhybridized orbitals, they can be empty as they are in BF3, the example we went through earlier, or those unhybridized p orbitals can overlap with other unhybridized p orbitals to form what's called a pi bond. So the way it works is, again, it's a side-to-side overlap. So you have two p orbitals that are arranged like this on your two different atoms. And then they combine, and so you're going to have a bond between the two atoms, and these are going to overlap side to side, where you're going to have that shared electron density between the two orbitals that overlap is going to be above and below the direction of the bond, the axis of the bond. So that's what a pi bond is. You're taking two orbitals and they're coming side to each other. They're two p orbitals, as I'm shown here, and so they're going to overlap above and below. The two regions that have the same phase are going to overlap with each other on the top and on the bottom, and that's going to be what's called a pi bond. All right, and so in order to form pi bonds, as I said, you need unhybridized p orbitals. They have to be orbitals that are not involved in hybridization in making those sp, sp2, or sp3, or whatever. They have to be unhybridized, pure p orbitals. So the main thing you're going to have to be able to do with sigma and pi bonding is using valence bond theory, predicting how many of each you have. So you'd have a structure of a molecule given, or the one that you've produced, and we ask you, how many sigma bonds are there? How many pi bonds are there? And that's kind of the level that you're going to mostly be examined on for things you'll do in the assessments for this course. So for single bonds, if you have a single bond in your structure, all single bonds are sigma bonds from the standpoint of valence bond theory. We'll see that's not quite right when we talk about molecular orbital theory next, but for valence bond theory, you would predict that any single bond you have between two atoms is a sigma bond. That's, again, the head-to-head overlap of the two orbitals that are involved in making that bond. Now, if you have multiple bonds, those would be double bonds or triple bonds, they're going to always have one sigma bond as well, but the rest are going to be pi bonds. All right, and so the way that multiple bonds work is you're going to have hybrid orbitals overlapping to make that sigma bond, but then you're going to also have unhybridized p orbitals overlapping to make 1 or 2 pi bonds. All right, so if you have a double bond in your structure, bond order of 2, that's going to be 1 sigma and 1 pi, so the 2 bonds are going to be 1 of each, sigma and pi for that double bond. If you have a triple bond, you still only have 1 bond that's sigma, and now 2 pi bonds to form the rest of those 3 bonds for the triple bond. So it's always, for a multiple bond, a double bond, or triple bond, it's always going to be 1 sigma, and the rest are going to be pi. That's how it's going to be for the predictions you make. And that's, in terms of predicting the bonds and what type they are, that's really the level you need to go to. So let's just close off with one more example where we're going to take the same molecule that we just talked about. Earlier we showed you how to complete the Lewis structure if we gave you the sort of incomplete structure. We predicted the hybridization for all the carbon atoms. Now what we're going to ask you is how many sigma and pi bonds are there in this molecule below. All right, so if we look at the structure, it's already drawn. We left off the lone pairs here, but for predicting bonds, it doesn't really matter. And we want to figure out how many sigma and how many pi bonds there are. So first let's go through to all the single bonds. Those are sigma bonds. So that's sigma, 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 sigma. Any single bond with just a single line is a sigma bond. A little bit of a tongue twister, single bond, sigma. And so all those are sigma. That's all of our single bonds. And then if we go to the multiple bonds in this structure, there's 3 multiple bonds. Each multiple bond is going to be 1 sigma, and the rest of that multiple bond will be pi bonds. All right, so you're going to have a sigma bond there and a pi bond to make a double bond, 1 of each. Another double bond, that's 1 sigma and 1 pi. And then the triple bond is going to be 1 sigma and 2 pi. Anytime you have a triple bond, it's 1 sigma and 2 pi. So if we count that up, assuming I didn't mess up my counting, we should have 15 sigma bonds in this structure and 4 pi bonds. So a total of 19 bonds overall, 19 lines drawn between the atoms, 15 of them are sigma and 4 are pi. And just to close out, the way that these pi bonds work, as I said, is if you have, let's see, how it was going. Let's do CO2. I might regret trying to draw this for you guys, but we'll see. All right, so for CO2, this is going to be an sp hybridized central atom. So I'm just kind of showing you a little more detail about how these pi bonds work. So you're going to have in CO2, oh man, let me try to draw this a little bit. I told you I regret trying to draw this for you guys at the very end. All right, so for CO2, we're going to have, those are going to be our sigma bonds, where we're going to have sp orbitals overlapping from carbon. So carbon is going to have those sp hybrid orbitals that are going to overlap to form the sigma bond. And then the pi bond is going to have unhybridized p orbitals overlapping above and below to make the double bond. And then the other one's going to be harder to draw because it's going to be perpendicular to this. So the unhybridized p orbitals, one of them is going to be vertical, one of them is going to be coming out towards you, so I'm not even going to try to draw it, but imagine you have another one on the other side that looks the same but is just rotated out towards you. So when you form multiple bonds like this, again, it really is a combination of sigma and pi. Sigma along the bond axis involving hybrid orbitals, pi bonds that are above and below the axis that are going to involve unhybridized 2p orbitals. So the pi bonds in CO2, or for a single carbon oxygen double bond, will involve hybrid orbitals for the sigma, unhybridized 2p for the pi, and both of those together combine to make the double bond that we just draw as 2 lines. So in reality, the double bond is not 2 identical bonds, it's 2 different bonds, a sigma and a pi, that combine to make that overall double bond. All right, any last questions before I wrap up? Okay, so hopefully I'll see all of you guys tomorrow at the exam review. And again, please get in touch with me if you have any last minute questions for next week's exam. Let me stop this real quick.